A confirmation about the audio, please, guys. If the audio is clear and available, we can see at night that the aspect of rainfall that is restricted, the cloud formation, etc., is restricted to few kilometers above the surface. Few of the dust particles are present even above that. Right, so that is something which is a localized phenomena, and rainfall is not something which is ever pervasive over a very large area. It is a restricted phenomena. Okay. And Earth has cooled down. Once cooled down is different for the planet. Earth's orbit as of now is very circular, as close as being circular as it can. And we have already talked about that every 1 lakh years, what is referred to as eccentricity, the planet goes through a very large elliptical orbit where it goes through significant phase of cooling. But now that has reduced to a kind of a circular phenomena, and again in a few in a few thousand years, again it will come into a cooling down phase. Okay, I hope that is understood. Trisha, I'm afraid of current affairs in the vast syllabus, but so is every other candidate along with you. This is not an isolated phenomena. So every candidate that you will come across, these are the two things that they are always afraid of. And even when you pinpoint the subjects that they will be afraid of, geography is also one of those subjects that candidates they get a scare about. So one by one, start capturing it and start conquering it. It is understand that it is a marathon, it is not a sprint race. The moment you understand that, you'll be able to have a much better grip on your preparation. And glacial till. It is not tilt, it is glacial till. And lateral moraines are same or different? No, both are very different. Yesterday also I told you that till is the deposit and moraine is a depositional feature. So for example, the riverine silt is a deposit, floodplain is a depositional feature. So there is a significant bit of difference. Okay. How to link current affairs? Basu, it is easy. The moment you are able to finish the portion of geography or any particular subject for that matter, then any news headline which comes for that particular subject, you'll be able to associate it with much greater amount of ease. For example, suppose in today's webinar, today's current affairs webinar which will be held, we shall be covering topics about oceans, and that is related to current affairs. But once you have understood the portion of oceans, you will always be able to relate to the portion of the current affairs coming with respect to that. Okay. Vivek, today I will not give map pointing. Tomorrow I'll give the map pointing again. Ankita, kindly tell me what you have studied in the last two classes. My dear friend, I have studied very different things, but what we have taught in the class is about the portion of geomorphology, and we had initiated the portion of climatology. Okay. Uni, kindly refer to the detailed schedule. You will get an idea. Is incoming shortwave radiation also called insulation? No, it is not called insulation. It is called insolation, solar insolation. We'll talk about it. Is Karevas in the Kashmir result of moraines? No, it is a result of a lacustrine deposit, a kind of a deposit which you find being done in the large lakes. That is what has formed the or resulted in the formation of Karevas. Many of the topic of map pointing is not explicit in the atlas, but then that is why I want you to explore those areas. If you can cite an example, I'll be able to help you out in a greater specific amount. And Nishant, I'm not feeling very confident, my dear friend. Again, the same as Trisha. It is something which every candidate goes through. It is only after one phase of complete revision of general studies, as early as you are able to complete that, that is when some confidence will come. Otherwise, you'll always be left chasing the syllabus. Um, How eskers are formed? Eskers are longitudinal deposits. So as a glacial movement happens, and we are talking about the continental glaciers, which move across the continental landmass rather than from the mountains. So as they end up moving, there are certain deposits of the glacial till which happens in a longitudinal manner, and that is what is referred to as an esker. I'm not able to find the Strait of Hormuz. Strait of Hormuz is okay. Locate Persian Gulf then. Okay, find out where is Persian Gulf and look at the region around Iran. River Rhine, take a look at Europe and take a look at the rivers. You will always have that. What kind of direction of wind movement in context of formation of tombolos, from land to sea or sea to land? So Kumari, it is basically what is referred to as a longshore wind, which moves parallel to the coastline. That is a very specific kind of wind movement which moves parallel to the coastline. Okay. Yes, Kamapati, that is correct. Yashi, note making from tab is required or not. That will depend upon how much you are able to perceive, how much you are able to retain. But if you are revising from tablet, I would always suggest to you, because the tablet videos have been in such a great detail, you can always take notes from that. Reading book by Majid Hussain for preparation, is that enough? So Majid Hussain is going to help you with the portion of Indian geography. And Indian geography, I would rather suggest to you that the portion of the basics you can cover from the classes and the additional reading materials or the basic book, and then please stick to the portion of current affairs. That will be much more rewarding than what Majid Hussain can contribute to that. Because see, how do you analyze the importance of a book? Many of the times the candidates come to us that, okay, few of the people have told us GC Leong, few of the people have told us Savinder Singh, few of the people have told us Majid Hussain. What should we follow? Always analyze whether a book is important or not based upon the previous year questions. Has there been any previous year question which has been present or to be found in Majid Hussain but not to be found in current affairs and NCRT? The answer is no. So that is why oftentimes I feel that Majid Hussain, if you are able to revise it frequently, then fair enough. You are open to explore as many books as you can. But please understand, any book, any text that you are exploring, explore it only if you have the capability to revise them endless amount of times. At least 5 times the revision should be carried out. Okay. Yes, Saurav, I will also be taking the sessions of Indian geography. Mayank, you can always use the tablet for revision. No, Palak, that will be sufficient. Okay. Periplanes are basically periplanes are basically those finally eroded and degraded regions where you have very few remaining portions which are not to be eroded or degraded. And for that, please understand that why I have not indulged in the discussion of pediplanes and pediments in general, because that is something for which you need to understand the cycle of erosion or the cycle of degradation. So there have been various theories provided, something required for your optional portion. There have been various theories regarding the cycle of erosion provided by uh, Peng, Davis, as well as by King. So there, all of them, they have talked about the fact that any land area, whatever might be the morphology or the shape of that land area, it will continue to get eroded unless and until that region is rendered to be a kind of a flattish one, where you don't have many of the materials to be eroded anymore. Be it a hill, be it a plateau, everything will be degraded and eroded eventually to the level of the sea. It might take a very, very long time, but once that is achieved, that is what is the condition of a peneplain. And thereby, you will observe that few of the regions, they will have a certain raised portions or a remaining portion which has not been eroded yet. That is what we refer to as monadnocks or inselbergs. Okay. And Abhishek, Nagorno, it is not Nagorno Karabakh, it is Nagorno Karabakh. Nagorno Karabakh is basically, observe the region between Armenia and Azerbaijan and take a look at the political map. That is an oil rich area where there has been a lot of war and dispute about. And recently, if you have been following current affairs, Azerbaijan had summoned Indian ambassador, and in order to complain that India has been supplying weapons to Armenia, which Armenia has been using punitively against Azerbaijan. So it is very much associated with current affairs. Okay. And right, most of the type of questions I have taken. Right. So now we initiate the discussion. Chavan, my dear friend, I am unable to look at your question. Your question is not visible as of now. So I'll try to take it up at the end, if that is fine. Uh, yes, Mayank, that will be sufficient. So now we continue with our portion of climatology and the discussion of the basics of climatology that we had initiated yesterday. So basically, till now, what is it that we had covered in the portion of climatology? We had basically talked about what do we understand by atmosphere, what is understood by the evolution of atmosphere, and how is it that the atmosphere that we see today, that is not the atmosphere that the planet had formed at the time of its formation. And the atmosphere has basically evolved quite significantly. From the very initial stages when the atmosphere was just composed of hydrogen and helium and so very light materials, to the present day where the atmosphere has got various distinct kind of gases, it has been a kind of an evolutionary journey. We also try to understand what is the greenhouse effect and how is it that the greenhouse effect is leading to global warming. We have talked about the benefits of greenhouse effect. We have talked about the aspect of and when we were discussing about it, we had discussed about the short wave radiation, the long wave radiation, the basic aspects of that. And we had also concentrated upon the constituents and the components which make up the atmosphere and the individual role played by all of them. So now today we continue with the portion of certain basic concepts, and we will introduce ourselves to these basic concepts as of now. Majority of these concepts you would already have studied up till your class 8th or ninth basic science. It is just about a recap of those things. So that is what we are going to concentrate upon as we move ahead today. And then we are going to finalize or understand in detail about certain other concepts of insolation, temperature, temperature inversion, urban heat island. What do we understand by lapse rate? What is adiabatic process? All these various technical terms and these technical concepts we are going to introduce ourselves with today. So we will start with the portion of modes of heating. How is it that the atmosphere is heated up? What is the process of the heating of the atmosphere? So remember, yesterday we had in the final portions of the session, we have had a discussion about how whenever you have a solid surface, that solid surface will receive much substantial amount of heat as compared to any of the air which lies in between. So even when we talk about the solar radiation which comes in, the short wave radiation which comes in, it passes through the portion of the atmosphere. It does provide atmosphere with some amount of energy, but significant heating is not caused by that phenomena. Why? Because when we talk about atmosphere, the gases, they are free to move. The molecules of the atmosphere, they are gaseous molecules. Now they are free to move from one region to another. Okay, so that is why for in one place, if they stick for a longer time, there will be a lasting heating which will be observed. But when we talk about a solid surface, it ends up receiving significant amount of heat, and the solid particles, they cannot move from one place to another. So that is why the solid gets heated quite significantly. So basically, when you have the solar insolation which comes in, or the solar radiation rather which comes in, now that solar radiation basically heats up the planet's surface. The planet's surface is heated quite significantly, right? And then once the planet's surface is heated, so suppose this is the surface, let's assume this is a blanket of air, or what we refer to as the atmosphere. Now if the solar insolation is coming through, now that solar insolation will hit the ground and will heat up the ground surface quite significantly. The ground surface will be significantly heated up. So once this heats up, then what will happen? Now, then you have various particles of air which are in contact with the ground surface. I hope we are aware of the basic meaning of conduction, convection. Is there any doubt which prevails in that area? Or I hope we are comfortable with that. Very good. Conduction is when the transfer of heat takes place when two objects are in contact with each other. That is the transfer of heat, which we refer to as conduction. Convection takes place when there is a transfer of heat by the movement of the particles. Remember the convection current that we studied in the portion of mantle? So that is your convection. So in conduction, the heat transfer takes place by the object. So for example, let's suppose you have a long iron rod. Now one portion of the iron rod is placed on fire. Now, slowly and steadily, if you even if you are holding the other end of the iron rod, you'll feel that heat after some time. Now, that transfer of heat through the iron rod has taken place how? By the particles which are in contact with each other. That is conduction, right? When you boil water in any particular pan or utensil, now there, the top portion of the water is heated up by the transfer of the molecules, by the movement of the molecules. That is what we refer to as convection. So that is how you have conduction and convection being able to transfer heat. Okay. So here, when we talk about, let's say, the ground first of all heats up, right? And then the air molecules in contact with the ground, in contact with the ground surface, they will also get heated up because they are in contact with the ground surface, right? So they get heated. How? By the process of conduction. Now, once the air molecules have been heated up, what will happen to the air molecules? Let's suppose you consider any parcel of air, any sample of air. In case you get confused by the term parcel, any sample of air. Now, once that gets heated up, the process will be very, very similar to what we have seen in the case of the heating experiment that we carried out, where we saw that in a kind of a utensil which you keep over fire, let's suppose you keep it over fire. Now, let's suppose you have filled it with water and you are actually trying to heat up water. So, what happens initially? You have the bubbles which are formed at the base, because it is the base which gets heated up first. And then these bubbles will, or the heated water will travel, and there will be a convection current, isn't it? Similarly, when we talk about the air particles, once they get heated up, now what is heat? Heat, in simple terms, is a kind of energy, is one of the methodologies by which energy is to be provided. Now, once let's suppose there is a significant amount of heat which has been provided. Now, that is energy. So the particles will gain a lot of energy. So the particles will start moving. Whenever you have a lot of energy, you start moving here and there. So the particles will start moving. So many of the particles, maybe they will escape from their earlier position. It can happen. So what will happen to this sample or parcel of air then? It will become lighter. We can say that this parcel of air will get lighter. And once this parcel of air gets lighter, then it will start rising up. Till when will it rise up? As long as it is warmer than the surrounding, it will be lighter than the surrounding. So it will continue to rise up, isn't it? So here, basically, the air parcel or the air sample gains energy becomes lighter and rises up. Okay, it will rise up due to the process of convection. So that is where the warm air starts rising up. And as the warm air is rising up, it will basically heat up the surrounding, isn't it? That there is a warm air which is rising up, so it will continue to lose heat to its surrounding. So the surrounding will also start getting heated up. So that is how you will have surrounding air starts gets heated up. Okay, that is basically the methodology of heat transfer. So how is it that the atmosphere gets heated? The lowest portion of it. First of all, heat will be received by the ground surface. The ground surface will heat up. Now it will start heating the air particles immediately above it. Now the air particles immediately above it, when they get heated, then they will gain energy, they will start vibrating, they will start moving, might escape their system. So the air parcel or the air column or any air sample will get lighter because the particles have escaped. And it is warmer, so warm air is always lighter, so it will start to rise up. As it rises up, it will basically heat up the surrounding air. So it won't be incorrect to say that the lowest portion of the atmosphere gets heated from the ground surface. That is its prime source of getting heated up. Now, think about it. All those of you who are unable to imagine about the rising air, I hope you would have seen a hot air balloon. You would have seen a hot air balloon in motion. That how is it that the hot air balloon actually ends up moving? You provide hot gases into the balloon where the balloon gets inflated and it continues to rise up, isn't it? So anything which is warmer will always get lighter because the particles have a kind of a motion, they will escape the system, and then it continues to rise up. And that is how the surrounding air gets heated. Now, after this, we come to the portion of another methodology of heat transfer, which is much more important in heating of the atmosphere, particularly at the ground surface, and that is what we refer to as advection. So, what do we understand by advection here? Advection is basically the transfer of heat by the horizontal motion of air. Advection overall talks about the horizontal movement of the air. In convection, you have a vertical rise or vertical fall of air column. Here you have the horizontal movement of air. So the transfer of heat through horizontal movement of air is called advection. So how does that happen? So many of the times you would have basically experienced that it is very hot, very warm, and suddenly a cold or a cool breeze passes by and the temperature becomes quite moderate and quite cooler. Now that cooling has happened. Why? Because a colder air has passed by. Similarly, during the winter months, it might be very, very chilly, but again, sometimes you observe the warm winds blowing and that warms up the region. During the summer months, peak of the summer, especially in the northern and in the northern part of the country, you have very hot and warm winds blowing in the late afternoon, and that is what we refer to as lu, isn't it? So that is what you have as, again, a method of advection. So that heat transfer by the horizontal movement of the air, that is referred to as advection. Now it can happen because of certain conditions. So for example, let's suppose you have a ground surface. Now let's suppose this is a region which is cold, and let's suppose this is a region which is warm. So if you have movement of winds from cold to warm, it will cool down the region, isn't it? Cools the region. right? Now that is what is referred to as cold advection. And the vice versa will also happen. That is, sometimes you will have a warmer area. Let's suppose this is warm and this is cold. So here you have, if a wind moves from a warmer region to a colder region, it will warm up the area, isn't it? Warms the region. So that is why you have a kind of a heat, and that is how you have a kind of a heat transfer. Just the simple winds that you experience. You do not experience a sinking air. That is something we cannot experience. We cannot experience a rising air in majority of the cases. In few of the cases, you can experience even that rise of the air, but that is very rare phenomena. In general, you will observe the horizontal movement of the wind itself, isn't it? So that is your advection. Now, horizontal movement of air is relatively more important than the vertical movement. For what? For transfer of heat. It is much more effective medium for transfer and distribution of heat from one region of the planet to the other area of the planet. So this is much more important than the vertical movement for transfer of heat and distribution of heat from one region to another. Okay. Now, here you have two kinds of advection. You have what is referred to as a cold advection, and you also have what is referred to as warm advection. Cold advection is a process in which the winds blow from a region of cold air to a region of warmer air, which results in cooling of the warmer region. And that will bring about a cooling of the temperature. Whereas when we talk about warm advection, it is the opposite of it, where you have winds, warm winds which are blowing. So warm advection is a process in which wind blows from a region of warm air to a region of cooler air. So warms a region. Okay. So you have various different, when we study about winds in the next module, we will basically be exposed to the aspect of cold winds as well, warm winds as well, that why is it and where is it that the warm winds blow, where is it that the cold winds blow. All of that we will be studying when we study more about the winds and the existence of winds in itself. But once we have understood the portion of advection and the method of heat transfer, let us understand how is it that heat ends up getting distributed from the lower region of the atmosphere to the upper region in the lower portion of the atmosphere itself. We are not talking about the uppermost region of the atmosphere. We are still very much concentrated on the lower portion of the atmosphere, which we refer to as troposphere. So basically, as you move up in height, in general conditions, you will come across a change in temperature. There is always going to be a change in temperature. And that is what is referred to as lapse rate. So, as you move across the height in a particular region of the atmosphere, the change in temperature that you experience, that is referred to as lapse rate. So, it is the rate of change of temperature as one moves higher up in the atmosphere. Now, the change in temperature, either the temperature will get colder as you move higher up, or the temperature sometimes can get warmer in certain areas of the atmosphere, or the temperature might not indicate any change at all. So accordingly, you have three different types of lapse rates. You have what is referred to as a positive lapse rate, negative lapse rate, and also zero lapse rate. Okay. Please explain lapse rate again. I am not done explaining lapse rate, my dear friend. Have some patience. And air travels from high pressure to low pressure. How will cold advection occur? That is why I like the smart students so much. So, just now I mentioned that we will talk about the wind and we will then be aware about how is it that the advection happens, how is it that cold advection happens, warm advection happens. But I'm sure that is something that you would have missed out. So, let me tell you again that we will study about the winds, and there is a cold advection, there is a warm advection. If you can simply hold your patience for one few more hours, we will be talking about what is the condition of a high pressure, what is the condition of a low pressure. But just to tell you what you have asked, mostly you will find cold advection because the colder region is that of a high pressure, warmer region is that of a low pressure. So mostly you will find cold advection in place, right? But there are conditions of warm advection as well. So please hold your horses, have patience. We will cover it and then you will be able to understand it better. Now, positive lapse rate. What is positive lapse rate? This is a condition when the temperature reduces with the increase in altitude. That is, when temperature reduces with an increase in height. That condition is referred to as a positive lapse rate. Why it happens? We'll talk about it. Negative lapse rate. When temperature increases with an increase in altitude. In height. That is your negative lapse rate. And then zero lapse rate. In certain conditions, in certain areas of the atmosphere, we have zero change as you move up in altitude. So when temperature is consistent or is same with height. So these are your types of lapse rate. What is lapse rate? So as you move a or as you move up a distance across the atmosphere, you will experience a change in temperature. Sometimes it can decrease. Why it will decrease? We'll talk about it. Sometimes it can even increase. Why it will increase? We'll talk about it. And sometimes it can remain the same. That is what is referred to as the lapse rate. Now, in the lowest layer of the atmosphere, what we refer to as the troposphere, we all are surrounded by the layer of the atmosphere that is troposphere. And we'll study about it that the height of the troposphere is roughly around 16 kilometers or 13 to 16 kilometers from the Earth's surface. So, in troposphere, we come across what is referred to as a positive lapse rate. That means in troposphere, as we move up in height, the temperature indicates a decrease. So this is where in troposphere, there is positive lapse rate. So here, why? Why is it that the temperature decreases as you move higher up? You would have experienced this, or in general, when you see a mountain peak, on top of the mountain peak, like let's suppose the top of many of the peaks in Himalayas, the temperature starts to reduce quite significantly. Whenever you would have gone to a kind of a hill station, you would have observed that the hill station is cooler, right? Have you ever thought about it, that why is it that the hill station is significantly cooler? That is because the temperature reduces with height. Why is it that the top of the mountain is covered with ice? That is because the temperature is reduced quite significantly. In fact, if ever and whenever next time when you travel in an airplane And if you notice, in case the pilot announces to you what are the conditions outside, if you notice, they will announce to you that the air temperature outside is minus 44 degrees Celsius, minus 50 degrees Celsius. So while on the ground surface you would experience a temperature of 35-40 degrees Celsius, higher up the temperature can be so very low. Why is it so? So there are multiple reasons for that. First is, now we know that the density of the atmosphere is going to be maximum where? Where is it that the density of atmosphere is going to be maximum? Very good. Closest to the Earth's surface, near the ground surface, that is where the density is going to be maximum, isn't it? Now, wherever you have a greatest density, and why is it that the density is highest at the ground surface? Because of the gravitational pull of attraction. It will pull in all the various different gaseous molecules, water vapor, dust particles, etc. Now, all these particles, they will be trapping significant amount of heat amongst themselves. All of them will be retaining significant amount of heat. So that is why heat retained in the lower regions will be much higher. Whereas in the upper portion, because the density of air is not so much, heat retained will also be slightly lesser. Then the other factor, we have talked about the fact that the atmosphere gets heated up primarily from where? From the ground surface. By the method of conduction and convection, the atmosphere gets primarily heated up. So as you move away from the source of heat, that is the ground surface, there will be a cooling down as well, isn't it? So first reason is, when, or rather, ground surface serves as a prime source of heating for the atmosphere. So farther away one moves, cooler it gets. This is one of the reasons. Second reason is, density is maximum near the ground surface due to the influence of gravity. So greater density of particles means greater retention of heat, isn't it? So density increases is maximum near the ground surface, which means greater retention of heat. Okay, that means there is a greater retention of heat by these particles. Hence, the lower portion will be much warmer, right? That means lower portion of air is much warmer. Why? Because there's a greater retention of heat. So why is it that the lower portion of the atmosphere is the warmest in terms of when you compare only the troposphere? That is because, first of all, the ground surface serves as a prime source of heat, right? The solar insolation is not able to heat it that much in the lower regions, but the ground surface that gets heated up, and then the air being in contact will also get heated up. So farther away that you move from the ground surface, you are moving farther away from the source of heat. Hence, the temperature reduces as you move higher up. Now, after this, by the way, we'll talk about the negative lapse rate and when is it that the negative and zero lapse rate occurs when we talk about the layers of atmosphere. So have some patience for that. Just as of now, understand what is meant by negative lapse rate, what is meant by zero lapse rate. Let us explore this positive lapse rate a bit. So when we talk about this positive lapse rate, here, that basically tells us that as we move higher up from the ground surface, the temperature will reduce. Now, this is a common phenomena that you experience all across the ground surface of the planet. So that is why this is what is also referred to as a normal lapse rate or an environmental lapse rate. This is what we refer to as a normal lapse rate. So under normal conditions, you experience that as you move higher up, with every kilometer that you move in height, the temperature reduces by 6.5 degrees Celsius. Right. So that is what you experience. So normal lapse rate or environmental lapse rate is what is experienced under normal conditions. That is 6.5 degrees Celsius of reduction per kilometer. So that means if you are on a ground surface having a temperature of 20 degrees C at the ground, as you move 1 kilometer higher up, the temperature will be 13.5 degrees Celsius. As you move 2 kilometers higher up, the temperature will be around 7 degrees Celsius. And like that, it continues to reduce. That is your normal lapse rate or environmental lapse rate. Now, here, when we talk about the reduction in temperature, will that be common across the entirety of the surface of the planet, or will that be variable? It is something which is never going to be consistent. How the temperature reduces as you move higher up, that is never going to be consistent across different places. Why? Because the constitution of air in itself, let's suppose you are right now present in Delhi. Now, the constitution of air above Delhi is going to be very different from the composition, or significantly different as compared to the composition maybe over Bay of Bengal, which might be quite different from the region of Rajasthan, isn't it? If let's say I compare two regions such as Bay of Bengal and Rajasthan, simply I can say without analyzing much, I can simply say that the amount of water vapor above these areas, they will also be different, isn't it? Above Rajasthan, the amount of water vapor, that is the desert area, the amount of water vapor will be very less in the air. And when we talk about Bay of Bengal, that will be laden with water vapor because of evaporation. Now, what do we know about the capacity of water vapor when it comes to heat? Can water vapor retain heat, or will water vapor not be able to retain heat? What is it that we studied yesterday? Let me know. Good, very good. Water vapor can retain heat. That is how it also contributes to the greenhouse effect, isn't it? So that is where you have the concept where above a drier region, the rate of temperature change, or the norm or the lapse rate that you encounter over a dry area, is going to be sufficiently different from a region which has got large amount of moisture which is present. Okay, so the rate at which the temperature falls over a drier area will be different as compared to the region where you have moist air. How and what will be the difference? So let us understand that. So basically, this is your environmental lapse rate. It is the rate at which the temperatures change with an increase or a decrease in altitude. It is the vertical distribution of temperature of a given geographical location at a particular period. If the lapse rate is positive, the temperature decreases with height as it usually does. If it is negative, the temperature increases with height, what we also refer to as temperature inversion, which is something we'll introduce ourselves at the later stage in this particular module. So here, when we talk about the different conditions, let's suppose we consider here a region which has got dry air, and here you have got moist air. Now, moist air means you have significant amount of water vapor which is present, isn't it? So you have significant amount of water vapor which is present here. Whereas over the region of the dry air, water vapor won't be present. And we do know water vapor is able to retain heat. Ashay, my dear friend, regardless of how many times you paste the same question that whether note making is important or not, always I will have the same question, same answer. And yesterday also I took out some time for the same doubt that whether PPTs are sufficient or not, or whether note making is to be required or not. That is dependent on your ability to revise, my dear friend. If you are able to retain everything, then why to make notes? Make a running notes. You have the recording of the videos also available. If you are unable to retain anything which has been covered in the class, then better to write it down. Right? I cannot be answering the same question again and again about what is required to be followed as a book list, what is required as whether do you need to have the note making or not. Is it understood now, or do you want me to write it down in before every class in the first slide itself, that what should be the procedure for note making, what are the books to be followed? If that is required, please convey it to us, that we will put it as a slide of PPT in every class. That is something which we have covered in significant detail in the first class, and we are covering it in every class. I'm devoting some time to answer this question, that whether note making is required, which book is required, which book is not required. And I'll tell you the general progression of it as well. After 10 days, the question will be whether this subject is important for UPSC or not, or can we do it without this subject itself. So please, whatever you are able to retain, try to retain it. Make a running notes if possible. If you are finding something which is not to be found in the PPT, make a running notes to keep yourself alive as well, to keep yourself awake as well. Always advisable to keep a pen and paper, and then make a running notes. It will help you to revise. Is that understood now? Right? Is that understood, or you still have doubt? Good. So now we come back to the topic. Here we talk about that moist air and dry air. So when we talk about moist air, it will have significant amount of water vapor which is present. Water vapor has got the basic capacity to retain heat. That is how water vapor is able to contribute to greenhouse effect as well, as we talked about yesterday. Now, let's think about it, and let's talk about a particular scenario. Let's suppose the ground temperature in both these cases is 30 degrees Celsius. Now, as you move 1 kilometer in either of these regions, as you move 1 kilometer in height in either of these areas. Now, in either of these areas, if you consider this, let's consider this section as A, let's consider this section as B. So, out of A and B, which of them do you think will be warmer at a height of 1 kilometer, given the condition of water vapor which is present? What do you think will be warmer? Ashay, you also think about it and let me know. Which will be warmer after a height of 1 kilometer? It will always be the side of B. This will be warmer. Why? Because here you have moist air. Here you have the presence of water vapor. And that presence of water vapor means it is able to retain heat. Right? So, because water vapor is able to retain heat, if you have greater presence of water vapor here, that means the heat which is emanated from, let's say, the ground surface, that will be trapped. Whereas in this case, that heat won't be trapped significantly and it will be lost. So that is why, as you move higher up in the region here where you have a lot of moisture, it will be much warmer. Is that understood? Also, always understand that it is the ability to retain and capture heat. When we have the moist air, big moist air means what? Lot of water vapor. Lot of water vapor means what? It will be able to retain heat. So that is why here there will be a greater retention of heat as compared to this portion. Here heat won't be retained. And if the heat is not retained means what? That heat will be lost eventually. So that is why here you will find it that the air is comparatively cooler, right? So this is what is referred to as the dry and the moist or the wet lapse rate. So that is when we talk about the dry lapse rate, when you have the air which is dry, so that is when you will experience that in the drier regions, the rate at which the temperature falls as you go higher up is quite significant. It is close to around 10 degrees Celsius per kilometer. Whereas when we talk about the moist lapse rate, it is around 5 degrees Celsius per kilometer, right? This is the reason why cloudy nights are always going to be warmer as compared to the clear skied nights. Always you will come across this experience that whenever you have had a cloudy night or there are a lot of clouds, lot of humidity, then it is comparatively warmer as compared during the night time as compared to the region which is dry. That is why even in desert areas the nighttime temperature goes very low, whereas in the moist areas in the coastal regions even the nighttime temperature is warmer, isn't it? So that is where you have the conditions where the lapse rate varies. So, in a way, if let's say you follow the height here, let's suppose you go here 2 kilometers higher up, 2 kilometers. Now, the temperature at the height of 2 kilometers will be somewhere around 10 degrees Celsius. Whereas in this case, the temperature 2 kilometers higher up will be how much? 20 degrees Celsius. Right? So that is the variation. Ideally, in practical scenario, in majority of the cases, neither this will be observed, neither this will be observed. You will always have certain regions experiencing, if it is the drier condition, it will experience a lapse rate of 7.5 degrees Celsius per kilometer. If it is bit moist, it will experience a lapse rate of around 5.5 to 6 degrees Celsius. So that is why the average is taken to be around 6.5 degrees Celsius per change in kilometer. And that is referred to as the normal lapse rate. Okay. Now, here, after this, we introduce ourselves. Now, negative and zero lapse rate, we will talk about it when we come to the layers of atmosphere and temperature inversion. Now, another thing that we introduce ourselves with is the adiabatic process. What is this adiabatic process? Now, even though this is something which all of us would have experienced at some stage or the other in our lives, from as simple a phenomena as, let's say, filling air in your bicycle tubes with the help of a pump. Most of you would have done that unless and until you had someone who would take your bicycle to get it filled and then bring that bicycle to you, and then you would privilege that bicycle by riding on it. Unless and until you belong to that category, most of us would have done that, especially in the childhood days. So here, what would you experience after filling a lot of air in that bicycle pump? You would have observed the basic thing that the bicycle pump starts getting heated up after some time, isn't it? That is an adiabatic process. So what is an adiabatic process? So till now we have seen the heating of the atmosphere, which takes place by the source of heat. But when the air gets heated from the ground surface or the air rises up and heats up the surrounding, that is a source of heat by which the air is getting heated up. But sometimes there is a change in temperature of air, not because there is an external source of heat which is provided, but simply by the change in volume of air. That is what is referred to as the adiabatic process. And another simple analogy of it will be understood or can be taken when you think about it in the form of energy. When you think about it, let's suppose if you can recall your school days or college days, whichever is easily relatable. So let's suppose you consider a classroom. Suppose your classroom had a capacity to handle 50 students. Now, those 50 students would sit there, they would talk, they would chatter. Whenever the teacher is not there, they would create a lot of noise as well. But then, imagine a scenario where you put all those 50 students in maybe a small storeroom or a smaller classroom, or you put those 50 students in a kind of a joint session with another set of class. If you recall those moments, what would have happened? The noise level would be very, very high. Why? Because now you have put in lot amount of energy in that same space, so the noise level would be very, very high. But then, if you, let's say you leave those 50 students in a large playground, whatever they are talking or even they are shouting, even that wouldn't be audible. Why? Because in a way you have expanded the space, allowed them to move as much as they can, so the energy overall has reduced. So the same phenomena is something which is observed in the case of air as well. How? Let us understand. So basically, here, let's suppose this is the air particle or the air parcel, any air sample that you consider. Okay. Now, each of the particles will have their own gravitational pull of attraction. They will have their own set of collisions that they are undergoing through. Now, let's suppose now every collision that any part, if I go to the science part of it, so every collision that the air molecules they carry on, they will produce some or the other amount of energy. Maybe that energy is something which we experience in the form of heat. So can we say greater the number of collisions that the air particles encounter, greater will be the temperature? I hope we are comfortable with this conclusion, that greater the number of collisions that the air particles encounter, greater will be the heat, greater will be the temperature. Everybody is comfortable with that? Right. So let us understand this basic concept. So let's suppose under certain conditions and due to certain conditions, I have reduced the volume in which these air particles are to be fitted. And I will also take a condition where, let's say, I have expanded the volume. Either conditions we will consider. So when I have reduced the volume, all the earlier particles will now be forced to fit themselves within this smaller volume. They will have to adjust, they will have to compress themselves in order to fit in that smaller volume. Just like combining two of the classes in one. So what will happen to the number of collisions as compared to the earlier case? Will the number of collisions increase or will the number of collisions decrease? What do you think? It will always increase, isn't it? Because now you have more number of particles, so the number of collisions would always increase. So what will happen to the energy produced? Energy produced will also be higher, isn't it? So here, number of collisions due to reduction in volume, number of collisions increase, and when the number of collisions increase means what? Greater energy produced, which means what? More heat. Or can we simply have the conclusion air gets heated. Isn't it? Now, let's suppose I have considered the case where the volume is expanded. So now these particles will have larger space for themselves, much larger space available for themselves. Now, in that larger space which is available for them, what do you think will happen to the number of collisions? Will it increase or will it reduce? It will reduce, isn't it? So, with the increase in volume, energy reduces. And what will this bring about? Air gets cooled. So, in either of these cases, whether we consider the heating of the air or if we consider the cooling of the air, now that heating and cooling has not come into place because it is in contact with a warmer surface or it is in contact with a colder surface. There is no heat source that we have considered in this discussion. So, this change in temperature which has happened primarily because of what? Because of the change in volume. That is what is referred to as the adiabatic process of heating and cooling. So these are those in which there is no net heat transfer between a system and its surrounding environment, or in simple terms, where the heating and cooling is attained purely by the change in volume. So heating is attained, heating or cooling happens purely due to change in volume. So we can also have another conclusion. Can we say that compression will lead to what? When we have compression of air, it will lead to heating. When we have, this is also what is referred to as adiabatic compression or adiabatic heating. And then when we have expansion of air, that would lead to cooling. But where do we experience this? Out there in the nature, where is it that we experience this? So while it is experienced in many of the cases, one of the easiest regions or the simplest areas where you can find an example of this is that of a mountainous region, right? So let's consider a mountainous area or a hilly area. Now, if there is a wind which is blowing like this, now as the wind encounters the slope of the mountain, the wind cannot penetrate through the mountain. Wind cannot say, no, I am very tired, so I'll not climb up the mountain. Wind cannot say that. So the wind will be forced to rise up. Now, as the wind is forced to rise up, can we say that it is moving into a region with lesser air density? Because the air density is maximum near the ground surface. So, can we say that as the wind rises up, it is entering into the area where the air density is less? So, if the air density is less, that wind will get a space to expand, isn't it? It will get a space to expand, and when it gets a space to expand, what will happen? Cooling will happen. So as it moves up, it goes through expansion and cooling. Expansion and cooling. So the wind is colder as it moves up the mountain slope. But after moving through the peak here, The wind will continue to flow. The wind will, it is not as if that mountain will provide the wind a kind of a launch pad where it will continue to rise up till the end of the planet and the end of the solar system. Eventually, after the mountain, the wind will follow the slope. So, here, as the wind comes down the slope, what happens? Can we say that as it is moving down the slope, it is going to an area where the air density is much higher, because the air density is much higher closer to the sea level. So we can always have the conclusion that as it is sliding down, it is coming into an area where the air density is significantly going to be higher, isn't it? So there, what does the wind have to do? In order to fit there, it will have to compress itself. When associate with it with any kind of travel that you would have done in a train or a bus, when it is almost empty, you actually take your own space, you spread your legs, you spread your hands, and then you relax, isn't it? But when if it is very crowded, then what do? You crouch, you basically try to compress yourself. So here also, the wind is going to an area where the density is going to be higher. So the wind will compress, it will go through compression and heating. So what will you have here? You will have warmer air. Not always, but in many of the cases, this is something that you observe. It is not something which is always going to happen. The temperature is going to increase by the time that you come from top of the mountain to the bottom. But it might not be quite drastic. It might happen that at the top, the temperature might be 0 degrees Celsius, and by the time that it comes to the bottom, it might increase to around 2 degrees Celsius. It might very well happen. So that is what is referred to as the adiabatic heating or cooling. I hope that is understood. Now, after this, here, when we talk about adiabatic cooling or heating, this is your definition for your consumption. So, when air is forced to rise up in the atmosphere, the air density and pressure reduces with height. As parcel of air will expand under this condition, so its temperature will fall due to fewer molecular collisions in the larger volume. Therefore, we experience a or observe a decrease in temperature. That is what is referred to as adiabatic cooling. Okay. Now, after that, when we talk about adiabatic heating, it results when a cooler, less dense air mass sinks and exhibits an increase in temperature. This is due to the molecules being forced to fit themselves into a smaller area and then having a kind of a collision. So, due to this, the molecules become agitated, start vibrating, and indicate an increase in heat. So, compression of air will always lead to heating, expansion of air will always bring about some amount of cooling. Okay, I hope that is understood. Now, after this, we come to the portion of the atmospheric structure, the layers of atmosphere. Now, this is a portion from which UPSC has been asking a lot of questions. And UPSC has been asking questions both in the mains as well as in the prelims exam nowadays. So, atmospheric structure is something where we have to understand the basic different layers of the atmosphere and their simple basic features. So, the atmosphere from the ground surface to the topmost portion, it is not going to be homogeneous. It is not having a homogeneous distribution. It is something where the density of the particles, etc., keeps on changing. The various impacts of heating and cooling also keeps on changing. So as there is a marked change in the difference, or there's a marked difference between the particles present, the temperature which varies, that is what determines the various different layers. So closest to the Earth's surface, you have the layer which is referred to as troposphere. Then further higher up, you have the stratosphere. Then higher up, you have the mesosphere. Then higher up, you have the thermosphere. And eventually, the particle density keeps on reducing, and then you have the exosphere, where eventually You don't have a particular boundary which demarcates the end of atmosphere. It simply dissipates into the outer space. Majority of all the climatic conditions and phenomena that we experience, that is a sum product of the troposphere itself. Our entire study of climatology that we are going to carry out, that is going to be dependent on or based upon the troposphere itself. Okay, so first of all, let us understand what do we have as this troposphere. So when we talk about troposphere, here it is the lowermost portion of the planet, in the sense of atmosphere, the lowermost portion of the atmosphere, which is sticking to the ground surface. Now, it is where the air density will be the maximum. The air that you and I we breathe in, that is the most dense air that we come across. As you move higher up, let's suppose even in the case of the mountains, as you move higher up, you will find that the air density starts reducing. That is why I know it is a kind of a derived and a tangent form, so I will not go into the depth of it. But just ever try to find out and do a research that people who live high in the mountains, who have indigenously and traditionally lived higher up in the mountains, they will have a different blood structure as compared to the people who have always lived in the plain areas, because the amount of oxygen available for them for their day to day use is going to be very different as compared to the ones who live at a sea level, right? Because the oxygen quantity, the amount of gases, etc., everything reduces. This is not to say that last year I had visited Shimla once, so has my blood or will my blood be different, or last year I went to Arunachal Pradesh once, so will my blood be different? No. Traditionally, you will find that those people who live high up in the altitudes, their bodies adapted to using lesser amount of oxygen from the atmosphere. So that is how even the body morphology, blood morphology, in a way, the RBC count, that changes, the hemoglobin count, that changes ever so slightly. So that is basically to tell you that the troposphere will have the maximum amount of density of air, and even that density is going to be maximum closest to the ground surface. So this troposphere consists of 80% of the mass of the, when you consider the presence of water vapor, dust particles, and even majority of the gases. There also you will find that majority of the air particles, they are present in the region of troposphere. Why? Because of gravitational pull of attraction. Now, the height of the troposphere is not consistent over different parts of the planet. The height of the troposphere is going to be maximum around the region of equator, around 5, 10 degrees, 20 degrees north and south of equator. And the height of troposphere is going to be very low when you talk about the region of the poles. Why is that? So for that, you have couple of reasons. So average height is 13 kilometer and extends roughly to a height of 8 kilometers above the poles and around 18 kilometers around the region of equator. Why is that? So the reasons. First, very good, Samir. So this is basically, first reason is a very simple one. So any area which gets heated up, any region which gets heated up, any portion of liquid which gets heated up, it will tend to rise or will it tend to sink? After getting heated up, will it tend to rise or will it tend to sink? It will tend to rise. In general, I hope we have this much amount of clue about different places of the planet, that the region of equator will be much hotter as compared to the region of the poles, isn't it? So, in the region of equator, there will be rising air column, whereas the region of the poles, which are very, very cold, generally the air column would be something which is naturally going to fall down because the ground surface is so very cold, isn't it? So, around equator, there is a rising convection of air. Whereas around poles, we have sinking air. Okay, that is something which is understood. Because around the region of equator, why do we have rising air? Because roughly that is the area which receives maximum amount of heat throughout the surface. That is around 30° north and south of equator. If you consider, that is the region which receives maximum amount of heat. So that is where you will have a rising air column. Whereas, so that is a rising convection current. So imagine if this is the troposphere, you have the rising air, it will continue to push the region of the troposphere further upwards. So that is why around the region of equator, you have a greater height. But when we talk about, so this is around the region of the equator having a greater height. Then also, you will observe that around the region of the poles, there is a slight amount of reduced height because that is where you have the sinking air. Now, secondly, another factor. So, Garvit, Coriolis force is absent at equator, my dear friend. So, the second factor is very simple, associated with this itself, and that is the gravitational pull of attraction. We do know that the planet is not consistently a sphere. Planet is not a complete sphere. So you have the polar regions which are ever so slightly closer to the region as compared to the equator. Equator is slightly bulged. As compared to the polar region, they are slightly flattened. So the gravitational pull of attraction will be much greater at the region of the poles as compared to the region of the equator. Why? Because the distance from the center, that varies ever so slightly. So always you will have the region of equator experiencing a lesser gravitational pull in comparison. So that is why you will have a basic kind of expansion. What is sinking air? Sinking air is basically wherever, let's suppose, even in convection, we have already talked about, isn't it? We have talked about a convection current earlier. That is somewhat like this. So this is what is your rising air column. So here it will push it up, but here as the air sinks, the height will be reduced, isn't it? That is the aspect of sinking air. So there is a slight variation in gravitational pull. Why there is a slight variation in the gravitational pull? Because of the very simple phenomena. If I can use this particular slide, if you talk about the planet is not a complete sphere, it is an oblate spheroid. So that means from the center, if you consider, the distance to the region of the poles is going to be lesser in comparison to the distance to the equator. This is slightly larger. So here, because the distance is larger, the pull of gravitation will be slightly smaller. I hope that is understood. So here, slight variation in gravitational pull, lesser at equator. So when the gravitational pull is lesser at equator, it will automatically expand. Now there is another basic factor which you can combine in the first point itself, or you can write as a separate point. And that is any object which is warmer, any object, when you heat that object, will it tend to expand or will it tend to contract or compress? What do you think? Any object which is hotter will always tend to expand, isn't it? And any object which is colder will tend to compress a bit. So the polar regions which experience very low temperature, the air above it will also be very, very cold. So it will compress itself ever so slightly. Whereas in the region of equator, there is significant amount of heat, so it will expand itself ever so slightly, isn't it? So equator is very hot, being very hot. As of now, I'm just taking the broader idea of equator. But please understand that the hottest regions of the planet, they will never be found at equator. They will be found around the slightly 20, 30 degrees north or south of equator. And we'll talk about the reasons about that as well when we understand or when we dip our teeth deeper into the portion of climatology. So as of now, we will just be referring to it as equator. Slowly and steadily, as you get exposed to more technicalities about climatology and air movement, how that rise happens, why that rise happens, then you will be able to understand that the hottest portion is not always at equator. So equator being very hot means air above it expands, whereas polar region being very cold means air above compresses a bit, isn't it? So all these can be cited as the reason why you will have a greater amount of volume or height in the region of the troposphere around the region of equator as compared to the region of the poles, where the height at the region of equator can be 16 to 18 kilometers from the surface, whereas the height around the poles will be around 8 to 9 kilometers from the surface. Now if I ask you a basic question, yes, Garvit, the first and the third points are almost similar. So if I ask you a basic question, that will this be consistent throughout the year or will this experience a seasonal change? What do you think? Will this height be consistent throughout the year or will this experience a seasonal change? Beautiful. Very good. So this will experience a seasonal change, because all throughout the year you won't have the same amount of heating and cooling of different portions. So because the height is dominated by the rising or the sinking air or the expansion or the compression of the air, so you will not always come across a kind of a variation, or you will not always come across a similarity in height. It will always experience a kind of a seasonal variation as well. Okay, but please understand, even though the first and the third points they appear to be similar, there is a minor difference. The difference is that in the first point, we have talked about the rising air, the movement of air particles. In the third point, we have simply talked about the expansion, where the molecules, they get heated up and they simply expand. And we have talked about compression as well. Now, another aspect here is about the vertical motions. So, here we have already talked about the fact that when the air gets warmer, that air tends to rise. Whenever air gets warmer, it will tend to rise. It will rise up till what point? As long as it is warmer than the surrounding. Why? Because warmer air is lighter. Why? Because warmer air means greater energy, means the particles will escape that system. So it is lighter than the surrounding. So whenever the air is warmer as compared to the higher level, the air will rise above. Now, in the region of troposphere, which observes a positive lapse rate, will you or will you not experience a vertical motion of air? What do you think? In the region of troposphere, will you or will you not experience a vertical motion of the air? Perfect. So here, because we have a positive lapse rate, means the lower region is warmer as compared to the upper region. So you will always experience a kind of a vertical rise of air. So vertical rise movement of air is very prominent. This is the reason why when we talk about large airplanes, not the smaller ones, the larger ones, which end up having a kind of an international distance covered or an intercontinental flights that you have. For example, you have the Boeing 747, 777s, the Airbus A380s, A350s, the larger ones. They will never be traveling through the region of troposphere. Majority of these larger airlines, they don't choose to travel through the, or the larger airplanes rather, they will never choose to travel through troposphere, because that is where you have significant vertical rise and fall of air. And whenever you have that vertical movement of air, immediately the airplane will experience turbulence, right? And in the larger airplanes, the turbulence is much more painful. So that is why the larger airplanes, in order to escape that turbulence, they will always be moving slightly above the region of troposphere. The smaller ones that you have, which generally all the airlines use for domestic travel, the smaller ones will be moving through upper region of troposphere, but the larger aircrafts, they would be moving through the lower region of stratosphere. Okay. Now, here, tropopause. Tropopause demarcates the end of troposphere. That is why the term pause. It is the end of troposphere and it demarcates where the stratosphere is going to begin. So we'll talk about tropopause for a bit, and it is that tropopause which will indicate a zero lapse rate. We'll talk about it, but before that, we introduce ourselves to the region of stratosphere. So when we talk about stratosphere, stratosphere is particularly unique, very unique. Stratosphere is where you have a very significant concentration or density of oxygen atoms present in different state. That is, normally oxygen is present in what form? O2, right? You would have heard about O2. That is the stable form of oxygen that is available for us to breathe. But the oxygen atoms, sometimes they have three atoms in a molecule. What is O3? What is referred to as ozone. So in the region of stratosphere, you have a particularly, so let's suppose this is your tropopause. This is your stratosphere. Now, in the region of stratosphere, you have a significantly thick layer consisting only of ozone molecules or very high density of ozone molecules, which is also referred to as ozonosphere. Now, ozonosphere is where you will have O3. This is what is also referred to as ozone layer, right? Now, why ozonosphere is very unique is because this is where the rays of the sun, the ultraviolet rays of the sun, they get absorbed and filtered out. Let's suppose you consider the UV rays, ultraviolet rays, which are not healthy for us. So these UV rays, they will get absorbed or simply pushed out. So in a way, ozone layer protects us from exposure to ultraviolet rays of the sun. Ultraviolet rays of the sun, they are neither beneficial for the plants, nor are they beneficial for the animals, nor for us humans. When we get exposed to too much amount of ultraviolet rays, that is where we have skin lesions, and in certain cases, it can even lead to skin cancer. So these are where your UV rays, they are reflected back. But significant amount of ultraviolet rays, They are moving through the ozone, they are getting absorbed by the ozone layer. So, what will happen to the temperature here? Temperature of ozonosphere, what do you think? Will the temperature get higher or will the ozone layer experience cooling? What do you think? Very good. Because it is also absorbing large amount of ultraviolet rays and also reflecting it back. So ozonosphere ends up absorbing huge amount of heat. So this is where large amount of heat is absorbed. Heating occurs. Now, just below the tropopause, we had a condition where we had a troposphere. Now, in the region of troposphere, by the time that you reach a height of 16 to 18 or 14 to 15 kilometers, apply the normal lapse rate, even the normal lapse rate, or let's assume a lapse rate of 7 that you apply. So if let's say we are talking about a height of around 14 degree or 15 degrees Celsius, the temperature would easily be minus 60, minus 80, right? So by the time that you reach the top of troposphere, the air is very cold. But here, heating is occurring, isn't it? Now, when heating is occurring, means the entire region of stratosphere warms up. This entire region warms up due to heating and presence of high concentration of UV rays. Okay. Now, in this situation, basically, what do you find? You will find that as you are moving, let's suppose you are an individual, somebody with the help of an airplane, let's suppose you have been put here. As you move higher up, what will happen to the temperature? The temperature will keep on increasing or will the temperature reduce as you move higher up? What do you think? Very good. The temperature will increase. And why? Because there is a greater amount of ultraviolet rays as you are moving higher up. So this is where you will experience a negative lapse rate. You will experience a negative lapse rate. That means rise in temperature with height. Now that means the air, when we consider the region of stratosphere, that means what? The lower region of stratosphere is cooler as compared to the upper region of stratosphere, which is warmer. I will repeat. Because the temperature rises with height, that means the lower region of stratosphere is cooler as compared to the higher region. So in that case, will you have a vertical motion which is induced? The vertical motion of the air. You won't come across that. That is why here you have very weak vertical motions, very weak vertical motions. Why? Because of the negative lapse rate, due to the negative lapse rate. And that is why larger commercial aircrafts, they will always be using the region of stratosphere, the lower region of stratosphere, in order to escape any kind of these vertical motions and sudden rise and sudden turbulences. Okay. Now, after this, let us concentrate a bit on the region of tropopause. Now, when you consider only the tropopause, consider only tropopause as a particular layer. Now, can we say that from beneath the troposphere the tropopause is getting cooled down? Can we say that? That from underneath the tropopause is getting cooled down, but from above it is getting heated up. So when there is simultaneous heating and cooling process taking place, what will happen to the temperature? Will the temperature change? No, because simultaneously heating is also happening, cooling is also happening from below. So that is why tropopause will always indicate a consistency of temperature, and tropopause, or in general even stratopause, mesopause, etc., they will experience a kind of a zero lapse rate. So here, when we talk about the tropopause, so can we say gets heated from above and cooled from below. That means no net change in temperature. And that means what? Is an indicator of zero lapse rate. Okay. So, just to give you an idea about it, I again will bring your attention back to this particular slide. So, here, observe that if at the base on the ground surface, if the temperature, let's say, is 15 or 18 degrees Celsius, observe how the temperature will reduce consistently as you move higher up in the region of troposphere. As you encounter the region of tropopause, the temperature might be minus 60 or even minus 80 degrees Celsius. But in the region of stratosphere, the temperature starts increasing again. By the time that you reach the top of stratosphere or the stratopause region, here the temperature is around 0 degrees Celsius. Right? So by the time that you have reached the top of stratosphere, the temperature is significantly higher as compared to the top of troposphere. Now, why? Because stratosphere has got a heat source. And what is that heat source? Ozonosphere. But again, as you move away from that heat source of ozonosphere, observe that in the region of the mesosphere, the temperature starts to reduce. Where by the time that you reach the top of mesosphere, the temperature can be as low as minus 80, minus 100 degrees Celsius. Again, further higher up that you go, you will experience this time the temperature rises again. But why does the temperature rise up again in the region of thermosphere? That is because by the time that you reach a height of 100 kilometers and above from the ground surface, the air density has reduced quite significantly. But more importantly, in this region, you will have an unadulterated solar rays which will continue to bombard this region. So you will have the solar rays consisting the X-rays portion also, ultraviolet rays also, infrared rays also. All of them will continue to bombard that. And as it continues to bombard that, that is why each of the particles will have much higher amount of energy. But then it is not as if these particles will be together in one large bulk. They will be dispersed around. That is why you experience this particular kind of a phenomena. So when we talk about mesosphere, mesosphere is at a height of around 50 to 80 kilometers. Now here, again, as you are moving away from the region of stratosphere, you are moving away from the heat source. So that is why here again, you will experience a kind of a positive lapse rate. Positive lapse rate. That means temperature reduces as you go higher up. By the time that you reach to the top of mesosphere, the temperature can be at a low variation of around minus 100 degrees Celsius. Now, there is another variation of it as well, and another way to look at it as well. If I consider only the region of mesosphere, let's consider only the mesosphere. It has a positive lapse rate. So if I consider two portions or three portions here, let's consider four portions. A, B, C, and D. Now you have to tell me whether my conclusion is correct or not. Temperature at A is greater than temperature at B, which is greater than temperature at C, which is greater than temperature at D. Is it a correct conclusion to make? Why no? Manikandan Chavan and Pooja also. Why no? I'm only considering the mesosphere. So in mesosphere, at the bottom of it, we have the stratosphere where the temperature can be 0 degrees Celsius, where at the top it can be minus 100 degrees Celsius. So we can say that the temperature at D is much lower as compared to temperature at A, isn't it? Now, that means as you are moving from D to A, you are encountering warmer air, right? As you are, let's say, moving from the position of D all the way to A, can we say that in this process, the air is something which will get warmer and warmer? So, this is the layer where the various different meteors, etc., the celestial bodies, the smaller ones, they burn up as they fall through this layer. Because as you have any of these meteors, let's suppose, which are falling, by the time that they are traveling through the region of the mesosphere, they get heated up and they start burning. And they are reduced to ashes by the time that they are basically coming to the region of stratosphere. So this is a layer where these meteors, meteorites, etc., they get burnt up as they come lower down. Okay. Why temperature increase in mesosphere? Temperature will not increase in mesosphere when we go up. Temperature decreases in mesosphere when we go up. Why? Because you are moving away from the source of heat, that is the stratosphere, that is the ozonosphere. Okay. Why they burned up? Because these will encounter warmer air as they start coming down. So when you encounter warmer air, there the temperature will rise and they will undergo a kind of a burning. Okay. Why does the, okay, so all of you had this, how fault formation would take place? Fault formation, Vivek, is for geomorphology. Kindly take a look at the recorded videos, you'll get an idea. So is the temperature at ozonosphere lower than the surface? Yes, in comparison to the surface, it is lower. Yes, right? So now we come to the portion of ionosphere, but before that, we'll take a break and we'll be back in 15 minutes. So we'll take a break and we'll be back and then we'll continue. If any plane would go there, start burning like meteor. No, see, the only reason that they burn up is as they are coming down with a velocity, they are encountering warmer air, which heats them up, and that is why they burn up. Okay. Why won't they burn at thermosphere itself? Because there the density is not high enough. Air density is not high enough. And anyways, as they are coming down, they are encountering cooler air. Okay. Right. So let's take a break and then we'll be back. Mission when we talk about the portion of air masses. Explanation of dry and wet lab, no vertical motion. So that is quite a significant one, Kambapati. You can take a look at the recordings. Just I'll tell you that in the case of the wet lapse rate, when we talk about there's a greater presence of water vapor means greater retention of heat in general. Lakshya, is advection also a type of a convection where fluid is air? In the larger context of things, sometimes you can consider it when you consider the permanent wind movement that we will study, but not always. Okay. Zero lapse rate, Lakshmi, is that condition where the temperature does not change as you move up in height. So in tropopause, from the lower portion there is a cold condition which is applied. From the higher condition, or from the higher portion of stratosphere, there is a warmer condition which is applied. So tropopause experiences a kind of a consistent temperature. That is why you have a zero lapse rate. Okay. uh, okay. So now we come to the portion of ionosphere, which is very much a part of thermosphere in itself. So when we talk about ionosphere, hot air balloon is very simple. That if ever you have at least seen a video of how a hot air balloon operates, you will observe that there's a fire which is lit that warms the air, and as the air warms up, warmer air fills that balloon, and then the balloon starts to rise up. So that is basically the portion, or that is how the uh, hot air balloon operates. So this was used to exemplify how is it that the warmer air is lighter and it rises up. Okay. And is tropopause called an isothermal zone? Yes. And why mesosphere is cooler? That is because you are moving away from the source of heat, and that is the heat of the ozonosphere. Hence, it starts becoming cooler as you move higher up. Okay. Why we have negative lapse rate in stratosphere? Because that is where a lot of heat is absorbed in the region of ozonosphere because of the ultraviolet rays. So ultraviolet rays being in larger density, that is why it is hotter. Okay. So now we talk about the ionosphere. Ionosphere is the region present higher up from the region of mesosphere. So ionosphere extends in the region of thermosphere, and in this area, while the density of air particles, they will start reducing, but here also you will have the presence of oxygen and nitrogen molecules. And these oxygen and nitrogen molecules, they will be hit by the unadulterated rate, or unfiltered rays of the sun. That means solar radiation will be at its maximum impact. So, because of that, the solar rays, when they hit these molecules or these atoms, many of the times, because of the large amount of energy, the electrons simply jump that. So, basically, if I'll show I'm sure all of us would have studied about what an atom is. But just to give you a simple example, so an atom will have a kind of a molecule, or a kind of a structure somewhat like this, right? Let's suppose as an example. So here, due to higher energy, sometimes the electrons will simply escape, or sometimes the electrons will jump into it. So what that means is that these individual atoms and molecules, they will start exhibiting a kind of a charge, right? So that is where these atoms and molecules, they will exhibit a kind of a charge, and that charged particles, they extend over a large area in the region of thermosphere. Now charged particles are what are also referred to as ions, and it is these ions which make up this entire region. And that is why the region in the lower portion of thermosphere, which extends up till a height of close to around 400 kilometers, that is what is referred to as ionosphere. So why is it referred to as ionosphere? Because it contains electrically charged particles known as ions. Why does it contain electrically charged particles? Because here you have the unfiltered rays of the sun hitting these particles individually, and they end up gaining a kind of a charge. Now, that is where, because you have significant amount of charge which is accumulated, they also help in transmission of radio waves. Right. So radio waves and radio communication, even though not that much prominent nowadays you have satellite communication. But if you flip back 20 years or 25 years, radio sets were a commonality in almost all the households. So it would be transmitted, the signals would be transmitted with the help of the radio waves. Even now, if let's say you are traveling, basically you hear about the radio, and if you are listening to the radio, it is those radio waves which get transmitted from the region of the entire ionosphere. So how is it that the transmission takes place? So let us understand that. So let's suppose here we consider the ground surface, and here we have the ionosphere. Ionosphere will consist of various different charges. Okay, it will consist of the charged particles. So that means if let's suppose you have a communication tower here, if let's suppose you have a transmission tower here, here you have the transmission. So the radio waves, they are basically transmitted from here, and then eventually, after they hit these charged particles, that is when they are reflected back. And then they are basically received by the receiving tower, and that is how you have the facilitation of radio communication. So, had these charged particles not been present, so this communication would not have been made possible. Now, this is the reason of, or this is the entire mechanism of the transmission and communication through radio waves in general. This is your ionosphere. The mobile phones that you have, that uses the satellite communication. Radio communication is not used in that. So that is how it is transmitted. Now, many of the times, if you ask your parents, if you ask your grandparents, anybody who would have regularly used the radio sets, if you have not experienced it yourself, you would have experienced, or they would have experienced if you ask them, that whenever it used to be very cloudy, lot of cloudy conditions, kind of a thunderstorm like condition, lightning, etc., means very thick density of clouds. Oftentimes, you would get cross connection. You would catch connection of the radio towers from areas which you are not trying to receive, right? And you would not receive the correct connection. And why would that be? That is because even the clouds, they have the charge. So sometimes if you would have a condition where, let's suppose, there would be a cloud, a very dense cloud, and the clouds generally also consist of charge, so they would start reflecting the radio waves here itself. So it is that presence of charged particles, and this would lead to cross communication and miscommunication in many of the ways. So that is the basis of radio communication carried out by ionosphere. So the presence of charged particles. Clouds lie in the portion of the troposphere, majority of the clouds. You have a few clouds, a very limited amount of clouds, which is referred to as stratospheric cloud, which you will find in stratosphere in very limited quantity. But otherwise, all the cloud types that you come across, that is in troposphere. So, presence of charged particles. Yes, clouds also have a charge. We will study about it later, that why the clouds have charge. And that is the reason why we experience thunder and lightning eventually. And Rajasthan, sometimes it connects to Pakistan radio channels. Yes, and if you go to West Bengal, you get Radio Bangla in the cases of whenever, or in the region of Uttar Pradesh, oftentimes you get the connection from Nepal, and that is oftentimes the cross connection which tends to happen. Now here, by the way, UPSC had asked a question about this, that why does radio, or why do the radio waves get reflected from the region of ionosphere? And that is because of the charged particles. It was a question of prelims, which we will discuss when we are going to discuss the previous year questions. Now, you will be very interested or intrigued to know that these charged particles, oftentimes, they end up interacting with the charged particles emitted by the sun as well. Because when we talk about the sun, and again, as you will study in the portion of science and tech, that sun also ends up emitting a lot of charge in the form of coronal mass ejection, solar flares, solar winds, etc. And these charges emitted by the sun, they end up traveling at a massive speed of hundreds of or many thousands of kilometers per second. And when they travel with such incredible speed, they end up interacting with these charged particles sometimes. When they do interact with these charged particles, obviously, the result is something which is very common and which is very expected, and that is all the radio communications, they are basically disturbed. Many of the times those charged particles emitted by the sun, they also end up influencing your electrical grids. Telecommunication is completely disrupted. But more importantly, they end up emitting light. When they interact with the charged particles, they end up emitting light. And that light is generally concentrated around the polar regions. And that light, which you observe close to the northern poles, that is what is referred to as the northern lights or aurora borealis. And those lights which you encounter, the same lights which you encounter in the region of the southern hemisphere, that is what is referred to as aurora australis or southern lights. Every year, lakhs of tourists, they do visit the region close to the northern and the southern poles in order to witness these very beautiful auroras or northern and southern lights. But why does it occur over the region of the poles? Does it occur in other areas? Very faint sometimes, but it is mostly dominant in the region of northern and southern poles. Why is it so? Beautiful, Garvit. Very nice. That is because of magnetism, geomagnetism. Magnetism, which is extended by the Earth's surface. So, here I'll explain it to you very briefly, as much as it is required for your basic understanding, and that is auroras. It is not Aurora, by the way. Aurora is a name title that we use in many parts of India. So please don't confuse it that he's saying Aurora Australis or Aurora and so on. No, it is Aurora. Okay, so please don't get confused in that. That is northern and southern lights. So basically, suppose you consider the sun. And let's suppose you consider the planet Earth. Now, when we talk about planet Earth, we do know that planet Earth oftentimes it behaves like a magnet. So, a bar magnet. So, that is why it does have its magnetic north and south poles. Okay, it will have magnetic north and south poles. Now, the greatest density of these magnetic field lines will be found in which place of the planet? The greatest density where these magnetic field lines are present in very high quantities, where all of them are converging and concentrating. In the region of the poles, very easy, right? So this is where you have the greatest density of the magnetic field lines. So once the charged particles, they are emitted by the sun, let's suppose. These charged particles, as they are emitted and as they are traveling through the vast expanse of space with an incredibly high speed. Now, what they will do as they travel, they will be automatically attracted towards the region where the magnetic field lines have the greatest density. Okay, they will be attracted towards these areas of higher latitudes where the density is very high. Now, it is here in these regions where these charged particles emitted by the sun, charged particles emitted by sun, that is where they end up encountering with these charged gaseous molecules which are present in the region of ionosphere and thermosphere in general. Which molecules do you think would be found in that particular region? When we say that molecules in the atmosphere, which molecules are we talking about? We are talking about oxygen and nitrogen molecules. So, oxygen and nitrogen molecules, which are present at that greater height, not in great density, in very reduced density, they get excited. And after some time, maybe the electron jumps back. So, they do get in their natural and neutral state once again. Every time that this happens, when they get excited or when they return into their natural state, that emits energy, and that energy is experienced in the form of light. And that is what we have in the northern portion. We have the northern lights, this interaction in this entire area and interaction in this entire area. This produces northern lights, which are also referred to as aurora borealis. Whereas in the southern hemisphere, this is referred to as southern lights, what are also referred to as aurora australis. Okay, so that is how you have the presence of these northern and the southern lights, which generally are encountered. And that is because once the charged particles emitted by the sun, they encounter with these or they get to interact with these atmospheric particles, that is oxygen and nitrogen molecules at a greater height, they will put them into an excited state or bring back them into their natural state. Every time that happens, energy is produced in the form of light, and that is where you get beautiful hues of green, bluish, sometimes even orange and pink color in terms of the lights which are emitted. And that is what is referred to as the northern and southern lights. Now, even these particles, they basically encounter, or these particles, they sometimes retain charge for permanent duration, sometimes they retain charge for a temporary duration. So that is what determines even the further subclassification of ionosphere into D layer, E layer, F layer, and so on. But that is not relevant for your GS, so you don't have to go into that particular detail. Okay. And what phenomena is experienced in Norway that attracts so many people for stargazing? That is what we are talking about, my dear friend. Auroras. Okay. Is that understood? If not understood, which portion is not understood? Can auroras be visible from India? Absolutely not. Are auroras harmful? Absolutely not. Okay. Interaction of charges part happens every day, not always. Whenever the sun will release charged particles, this is not a consistent phenomena. This is a periodic event. Whenever you come across a solar flare or a coronal mass ejection, all these solar events that you come across, that is when sometimes the sun releases a lot of these charged particles. Now, why do these charged particles interact only at the region of the poles? Because they are influenced by the gravitational field lines extended by the planet Earth. Now, gravitational field lines are present in maximum density around the polar region, and that is where they are redirected towards. So, these charged particles, when they encounter those oxygen and nitrogen molecules, they either will bring them in a charged state or return them into their neutral state. In either of the cases, those atoms and molecules will produce energy, which is reflected in the form of light, and that is what we refer to as the auroras. Okay, I hope that is understood. Now, after this, we move to the portion of insolation and temperature. Why these charged particles from sun only get attracted towards the poles? That is because that is where the magnetic field lines are at maximum density. Okay. Um, Nikki, please tell us about the tropospheric ozone too. That you will study in the portion of the ground level ozone, photochemical smog. You will study it in the portion of environment ecology. Okay. Now, after this, we come to the portion of insolation. What is insolation? The incoming solar radiation, which ends up heating a particular region, heating the surface, that is what is insolation. So, insolation is the amount of solar radiation received on a given surface at any given period of time. In any particular unit area, the total amount of solar rays which are received. Now, before any confusion, etc., is created, by the way, if you want to have a detailed look into this particular phenomena, I can direct you to a YouTube video that we have done, and that was about a peculiar event which happened, that is space hurricanes. So kindly, sir, if you want to look into the animation of these, search for the space hurricanes video on Byju's IS YouTube channel, and you will get an understanding of that in further detail. Okay. Now, here we come to the portion of insolation. Insolation is the total amount of solar rays which are received in any unit area by the ground surface or in the atmosphere. Now, insolation is not always going to define the temperature. That is, the total amount of solar rays received in an area is not always going to define the temperature of a region. But nonetheless, it is much more and is a very significant factor in contributing to the temperature change. So here, does not always determine the temperature experienced, but is an insolation is an important factor which contributes to variation or temperature experienced in a place. Okay. So, insolation received in various areas or the amount of solar radiation received in various areas, that also varies. And it is dependent on different factors. We'll take a look at that, the factors on which the insolation is dependent upon. But here, I want you to be aware of how is it or what is consisted of when we talk about a small weather station or a weather observatory. So, this is what a very small weather observatory will appear to look like. What you observe here in a kind of a cage like setup, that is what is a thermometer installation. This is where an air thermometer is installed. Generally, this is for temperature measurement. Thermometer. Because in order to measure the air temperature, you cannot keep the thermometer on the ground surface. Why? Because then, rather than showing the air temperature, it will indicate to you the ground surface temperature. So that is why thermometer is always suspended into the atmosphere, and it is suspended at a height of close to around 1 to 1.75 meters from the ground surface. That is where the air thermometer is basically subtended. And then here you also have what is referred to as an anemometer. This is again something that you would have observed significantly. What is an anemometer used for? Very good. For wind. This is for measurement of wind speed. Then here, what you have is an installation for a rain gauge. So how do you end up measuring the amount of rainfall received in an area? So you end up measuring the amount of rainfall with an equipment that is referred to as a rain gauge. So rain gauge is rather a simple construction where you will find that a large tumbler is kept. Okay. And on top of that tumbler, you will observe that a funnel is basically installed. A funnel like setup is kept. Now, what this funnel does, it basically accumulates any amount of water which is received, directs it into that rain gauge. And this will have its own measurements, scaling, right? And that is how eventually the total amount of rainfall received in any particular region, any particular day, that is measured. So this is your rain gauge to measure amount of rainfall. Okay. Rainfall is measured in centimeter or millimeter. That is the measurement parameter for the amount of rainfall which is received. Now let us take a look at the factors which end up influencing the variation in insolation in different particular regions of the planet. So here, when we talk about the various factors, one is the angle of inclination of the planet Earth. At what angle will you find the planet Earth to be inclined? So that means the various different places, they are exposed to various and varying amount of solar rays. How? We'll take a look into that. Then you have the revolution of Earth around its orbit. So that means you have the position of the planet that varies, its distance from the sun, that keeps on varying. So the amount of insolation received will also vary. So distance from the sun varies. So that means variation in insolation. And then you have the configuration of the land. Configuration of the land basically means the direction that the land is facing. Direction in which the land is faced. Means either towards the sun or away from the sun. Away from sun. Okay. And then you have the factor of altitude. Altitude means height. So where you have the variation in height, there also the amount of insolation will vary. What is insolation? Insolation is the solar radiation, as simple as that. Solar radiation which is received on the surface, that is referred to as insolation. Or the solar rays which are received on the surface, that is referred to as insolation. Okay, so that amount of solar rays received can vary in different areas. The amount of solar rays that you receive, let's say in India, that will never be the same as compared to the amount of solar rays you will receive in the poles or in the region of, let's say, northern Europe. Similarly, the amount of solar rays that you receive on the top of the mountain will never be similar to the amount of solar rays that you receive on the ground surface. The amount of solar rays that you receive on the northern side of any particular mountain, that will be different from the amount of solar rays that you receive in the southern side of the mountain, depending upon which is facing the sun. So that is basically the variation in solar rays. So let us understand what are the factors upon which the solar rays which are received in different regions, they end up varying. So first factor is the angle of inclination. Now, angle of inclination basically means that the planet is tilted on its axis at an angle of 23.5 degrees from vertical, 66.5 degrees from horizontal. So here you would observe that different areas, consider the different regions here. Different regions, they receive the solar rays with different angles, isn't it? They end up receiving the solar rays at different angles. So the power of the solar rays in each of them will end up varying. How? Let us understand that again with a torch example. So basically, here, when we talk about, let's suppose, the ground surface, let's suppose. Now let's assume you have a torchlight here. Okay. Now this torchlight is shining in this area directly in a way. And then let's suppose you have a torch which is kept here. Okay. Now this is shining its light in this particular region because it is tilted, isn't it? Now, this is torch A, this is torch B, right? Now here, out of A and B, which of these light which is thrown out of it, which of them will be more powerful, A or B? What do you think? Always B, isn't it? Why? Because it is falling directly, covering lesser distance. It is perpendicular. Whereas in this case, it covers a larger distance in the atmosphere as well. So it will be less powerful. So whenever you have a direct ray of the sun, that is, solar rays make close to 90 degrees as they fall. So here observe the solar rays, they are making close to 90 degrees. So that is where the insolation will be much more. Here you will have the lesser insolation. So if you can relate to it, early in the morning or late in the evening, when the sun is rising or the sun is about to set, the solar rays, are they powerful? No, you can in fact directly gaze into the sun itself. But try doing that at 12 or 1 in the noon when the sun is directly upwards. You won't be able to do that because your eyes will start burning. Isn't it? Why? Because they are very, very direct. Isn't it? So wherever you have the direct rays of the sun, they will end up receiving greater amount of solar insolation. So direct, or when the solar rays make a 90-degree angle or a higher angle of incidence, the solar rays are experienced to be more powerful. Okay, when the rays make a small angle, their impact is reduced. What does that mean? That basically means lower latitudes, that is the region closer to the equator in general, will always receive greater amount of insolation as compared to the region of higher latitudes, because in higher latitudes, they will make a very small angle, isn't it? So that means lower latitudes receive greater insolation as compared to the regions of higher latitude. Right? That is one of the factors which brings about a variation in the amount of insolation received in different areas of the planet. Then you have the factor of revolution of the planet Earth. So as the planet moves around the sun in its elliptical orbit, we have already seen in the first session itself that there will be areas which are going to be farthest, or there is going to be a position when the Earth is going to be the farthest away from the sun. There is going to be a position when the Earth is going to be the closest from the sun. When it is farthest, that is what is referred to as aphelion. And when it is the closest, that is what is referred to as perihelion. Here, the distance between them is not very significant. So, when it is farthest, that is the distance of around 152 million kilometers. When it is the closest, that distance is around 147 million kilometers. However, with the change in distance, the amount of insolation which is received, that also varies ever so slightly. So, when the Earth is closest to the sun, obviously it will end up receiving greater amount of solar rays or greater amount of insolation. So, planet receives greater insolation as or when it is closest to the sun, and vice versa is also true. However, this will not have a distinct impact on temperature, because remember, insolation is just one factor which contributes to temperature. Temperature is controlled by many of the other factors, including the axis of the planet, whether it is facing the sun, whether it is away from the sun, the movement of the wind, the type of the land surface. So, temperature in itself is dependent on many of the factors, insolation being just one of them. So, this is where it is, it does not have much impact on the temperature, as temperature is determined by many other factors. So basically, you have the planet Earth, which is closest to the sun when around January, that is 4th of January, when you will have the planet closest to the sun. And around the month of July is when it will be farthest away from the sun. So that is where you will have the perihelion and aphelion. So it is the 4th of July when it is going to be the farthest, 4th of January when it is going to be the closest, but it will not have much of an impact on temperature. Okay, so before you ask the question, but in July we have summer and you are saying it is the farthest, so it does not have much of an impact on temperature because temperature is contributed by many other factors. For example, here you will observe that in the month of July, it is the northern hemisphere which is tilted towards the sun, means for a greater part of the day, it will experience sunlight, and hence it is summer in the northern hemisphere in July. Whereas in the month of January, it is, even though it is the closest, in northern hemisphere you will experience winter because the northern hemisphere is tilted away from the sun. Okay, now can we witness January aphelion or well, or is this always July aphelion? No, it is always July aphelion. Okay. Now, then comes the configuration of land in terms of its aspect, or basically what it refers to is the direction in which the land is facing. So, for example, if you consider the planet, let's suppose, and here let's assume you represent the equator. Let's assume. Now, as the solar rays come in, so if I have a mountain here, this mountain will have a northern face, this mountain will also have a southern face. So in this case, which face of the mountain will receive more rays of the sun or more direct rays of the sun, the northern face or the southern face? Always the southern face, isn't it? So if similarly I have a mountain, let's suppose here, so this will be the southern face and this will be the northern face. So in that case, which will receive more direct rays of the sun? Northern or the southern face? The northern face. Very simple. So that is also how the solar insolation can vary from one region to another. This is the reason why when you talk about the Himalayas, the northern slope of the Himalayas, they don't receive that much amount of solar rays as compared to the southern slope. It is not as if this will be dark and this will be night condition. No, it will also experience sunlight, but then not the direct rays. It will be an indirect rays overall. So that is why, if you consider, and I want you to look at the orientation of Alps, the alignment of Alps in Europe, alignment of Himalayas in general. In both these regions, you will find that it is the southern face which faces direct rays of the sun. That is why the southern face of Alps as well as Himalayas, that is considered to be much more habitable. That is where lot larger significant amount of settlements happen because it is significantly and comparatively warmer. Okay, so the portion which is facing the sun, that will receive greater amount of insolation. Then we come to the factor of altitude, that is height. So when we go higher up, the amount of solar rays received is much higher as compared to when you are at the ground surface. Why is it so? So let us understand here. For example, let's suppose if you have this as the ground surface, let's consider a high plateau region like the Tibetan Plateau or any high mountain setup. Let's consider this. Tibetan Plateau on an average has got a height of 5 kilometers from the surface, isn't it? And let's suppose this is the top of atmosphere. Right. Now here, when the solar rays are going to come through, now, in which of these regions do they have to cover more distance? It is always going to be the region which is at sea level, this portion. There they have to cover much larger distance in the atmosphere. So the intensity will reduce significantly, isn't it? Here, the intensity of insolation or solar rays will always be higher. Intensity is always higher. And at the base, the intensity is significantly moderated. And before you guys start jumping again, that but you had just said that with height temperature reduces, and you are saying that solar rays are more significant. So again, I would like to remind you that insolation does not always determine the temperature. It is an important factor, but it does not end up determining the temperature in a region. So that is where temperature at a height is less, but insolation is more. So that is why when you take a look at any of the mountaineers, any of your colleagues, if ever they go for a mountaineering exercise, you will always find that they get sunburn. If they don't carry the proper protective equipments, they always suffer from sunburn. Right? Why? That is because there is a greater amount of solar insolation received at an altitude. Okay? Now, then we talk about the albedo. Albedo is the what is referred to as the reflective nature of any surface. So any surface that you encounter, they would not be reflecting light with the same quantity or in the same amount. The amount of light reflected will end up varying ever so slightly, right? So any surface that you encounter, the amount of light received and reflected will be different. For example, in front of your screen, you have two different surfaces. If I mark this as A, if I mark this as B, if let's say equal amount of light falls on both the surfaces, which of them do you think will reflect more? A will reflect more or B will reflect more? Always A, isn't it? So different surfaces, they have different amount of reflection capability. Now, that reflection capability is something which also ends up determining temperature over a period of time. How? We'll take a look at it. But before that, when we talk about albedo, it is the portion of solar energy reflected from the surface of the earth back into the atmosphere or back into space, the total amount of solar energy which is reflected. So let's suppose this albedo, it varies. Let's not suppose, this is the reality. So it varies between 0 to 1, where 0 indicates maximum absorption, no reflection, right? So 0 will always indicate no reflection, a complete black surface, no reflection. And this will indicate complete reflection, a white surface, for example. So, for example, when you consider the ice covered areas or the portions which are covered in significant amount of ice, this will end up having an albedo of close to around 0.85. That is the albedo. Means what? It means 85% of solar rays are reflected. Whereas this will have a general albedo of close to around 0.15 to 0.2. That means 20% is of solar rays get reflected. Okay, it varies from one particular region to another. Sometimes in ice covered areas, you'll find the albedo to be 0.9 as well in very rare cases, sometimes 0.8 on an average. So that basically is dependent upon the type of material, the nature of the rocks, etc. Now, here this is also a determinant of the temperature that a surface will exhibit or indicate. How? So, for example, let's consider any particular surface. Any particular surface, for example. Now, if this surface, let's suppose, has got an albedo here, or okay, we'll do this. So, let's consider two different conditions. We consider two different surfaces. So, in the first case, or A, let's suppose the albedo is 0.8. Now, in that case, almost 80% of the solar rays will be reflected, 20% is absorbed, right? 80% reflected, and you have 20% which is absorbed. And let's suppose we consider B with an albedo of around, let's suppose, 0.3. Means what? Of the total solar rays which are coming in, 30% is reflected, 70% is absorbed. Reflected, 70% is absorbed. Now, whichever surface will absorb greater amount of solar rays, it will also indicate a higher temperature overall, isn't it? Greater the absorption, greater is the temperature. Lesser the absorption means lesser is the temperature, isn't it? So, greater amount of solar rays which is reflected, amount of, or rather, greater amount of solar rays which is absorbed means higher the temperature. So always B will indicate a higher temperature, always, because it is absorbing 70% of the solar rays. That means lower the albedo, higher is the surface temperature. Right? Higher is the surface temperature. So that ends up determining the surface conditions or temperature conditions in many areas. For example, this is the reason why in hotter regions it is always advised to paint your house with a brighter color on the outside. So if your house or whichever building that you are living in, during the daytime, during the peak of the noon, if you go out and touch the wall, if it is, let's say, whitish, you will find that the walls are cooler. Why? Because the white surface will reflect majority of the solar rays. But let's suppose you go there and touch, let's suppose, the road surface, which is darker in color, darker in appearance. So that will be much hotter, significantly hotter. Why? Because it has absorbed significant proportions. So that is where it contributes to significant amount of temperature change. And that is why in summer season it is always prescribed to wear lighter clothes. In winter season, always prescribed to wear darker clothes, because the absorption amount is going to be distinctly different. Now, this is something which also is exacerbating or exaggerating the rate of melting of ice, particularly in the region of Arctic. The rate of melting has been accelerated because of this particular factor of albedo. How is it and why is it so? So, here, just by simple appearance, if I ask you that if I consider this area as A, or water, the solar rays are falling in, and if I consider the solar rays falling, let's suppose here at B on ice, where is it that you think that there will be greater absorption? What do you think? Always A will have a greater amount of absorption because it is darker in appearance, right? Greater absorption means higher temperature. That is what is exaggerating the rate of polar ice melt. How? Because of global warming, anyways, and atmospheric phenomena, anyways, the temperature is rising, leading to some amount of melting. But that kicks in a feedback mechanism. How? So, when you have the polar melting, let's suppose ice melt, and that ice melt is happening due to, let's suppose, global warming. Okay. Now, that will mean that water is exposed, or even thinner ice is exposed. Thinner ice, which is slightly whitish or transparent in appearance, that will also start absorbing more. So, water is exposed. And when water is exposed means lower albedo or greater absorption. And when you have a greater absorption means what? Higher temperature. And whenever you have higher temperature means what? Further ice melt will happen, and this process continues. That is the reason why in the region of Arctic, the rate at which the ice is melting has significantly accelerated. I hope that is understood. Okay? Right. Now, after this, we come to the portion of the basics of heating of land and water. How is it that the land and the region of the water, do they get heated at the same rate, or do they experience a different rate of heating and cooling? If so, why is it so? So for that, let us consider any land area. Let us consider a land area. Let us consider that land area having a kind of a water body as well here, right? So let's suppose here you have water. And by water, I'm not referring to the bucket that you have in your backyard, or the bucket that you have in your washroom, or the overhead tank that you are referring to. By land or a small lake or a pond that you have in your locality, I refer to the water region when I talk about it by seas and oceans, the larger water bodies. Okay. Now, here, when you talk about the solar rays and the solar insolation which starts coming in, the solar rays and insolation which start coming in. Now, in this case, when we talk about the land area, now, will the solar rays be able to penetrate the land area to a particular depth, or will the solar rays be restricted closer to the surface only? What do you think? Will they be restricted to the surface, or will they be able to penetrate to the depth of the land? Very good. It is a surface phenomena. So the solar rays in the land area, they will be restricted to 3 to 5 inches or lesser than that of the land surface there itself. But when we talk about a water body, in that water body, as the solar rays come in, they are distributed. Because water is slightly transparent, so they are distributed. On top of that, the water will indicate some or the other kind of movement or motion as well. You have ocean currents, upwelling, downwelling, etc., which are the events which happen in water. So the solar rays getting restricted to the topmost portion of the land. And in the case of the water, they get dispersed and distributed. Means which area will get heated much more easily? Land or water? Which will get heated much more easily? Always land? Always. Why? Because the heat is restricted to the surface itself. So it will get heated much more easily. So that brings us to the first conclusion. land gains heat at a much faster rate as compared to water. Okay. Now let's suppose it is night time, and both, let's say throughout the day, both of the regions have been heated up. Now it is night time. Now let's suppose they have some temperature. In the case of the land, that temperature is restricted to 3 to 5 centimeters or a few inches of the surface. Whereas in the case of the water, that temperature is distributed uniformly throughout. So when the night comes, that is when the regions or the surface starts losing heat. So which will lose heat faster? Land area where the heat is restricted to the surface, or the water where the heat is distributed throughout? What do you think? Again, land. Very good. Because in the case of the land, it is always restricted. So all that loss of heat has to happen only from the surface. Whereas in the case of the water, that loss of heat has to happen from the depths, from the various depths of the water. So it will take some time, isn't it? So here, land loses heat or cools down, loses heat or cools down at a much faster rate as compared to water. Right? So this is basic derivation, and this is the basic conclusion based upon which we are going to understand the various facets of the temperature distribution which happens during the day, during the night, during the summer, during the winter. So let us take care of these particular conclusions. So land gains heat at a much faster pace as compared to water. So during day, which of them will be warmer, land or water? What do you think? It will always be land, isn't it? Because the land is getting heated at a much faster pace. So during day, land is much warmer or hotter in comparison to water. Now, during night, night is when they have to lose temperature, they have to lose that heat. So which will be colder, land or water? Because we know that land loses heat at a much faster pace as compared to water. So which will lose heat faster and which will be colder? Always land, isn't it? That is why during night time, water is warmer as compared to the nearby land areas. Always. During night time, you will observe that the surface of the water is warmer as compared to the land area. So, water is warmer and land is much colder. Okay? Now, about the various seasons. So, when we say a summer season is a prolonged season of heat where heat is gained throughout the summer. It is heat which is gained. So, throughout the summer, on an average, which will have a higher temperature, land or water? Always land. Very good. So, here, on an average, land is much hotter, warmer, and water is cooler. Now, during winter, winter is when over a prolonged period of 2 to 3 months, you end up losing heat, isn't it? So, which will be colder in the months of the winter? Which will be colder, land or water? Always land will be colder because the land will lose heat at a much quicker pace. And here, please don't compare it that, but in the winter months, it is easier to stay on the land. But whenever I go to take a shower, the water is very cold. Again, I would say, please don't compare it to the overhead tank or the bucket of water that you have kept in your washroom or your backyard water pool, which is there. Always, when we talk about water, talk about the larger oceans and seas. So that is why during winter, land is much colder and water is warmer. Okay. It is based on this phenomena that UPSC had asked a question in prelims even this year. So it is this basic derivation which is going to help us quite significantly as we move ahead, as we talk about the land and the sea breeze, etc. It is going to help us significantly. Convection could be one of the reasons due to which water cools down late. And yes, convection is one of the reasons, yes, and also penetration. And in general, water has got a higher specific heat to talk about in very simple technical terms. So it will take a larger amount of temperature or larger amount of energy for the water to gain heat and also larger time for the water to lose heat. Okay. And last point not understood, that is land is much colder during winter. Land is much colder during winter because during winter the surface loses heat, so land will lose heat at a much quicker pace, and that is why water is going to be warmer. Something oceans also shine like stars. It is a reflection of light, reflection of moonlight. And that is what, if that is what you are talking about. Okay. Why in under ocean water is cool? We'll talk about it in oceanography. When we talk about the variation in temperature, or the conditions of thermohaline circulation, thermocline, halocline, we will talk about the temperature variation. Which among land and desert? Desert is also a land, my dear friend, isn't it? Or can we say that desert is water? Desert is also land. So that is where any land area you compare, this is your land, this is your water. Okay, land and sea breeze, will come to it. Deserts are hotter. Who told you? Who told you that deserts are? Are you aware that there are cold deserts in the world as well? That is what I was talking about yesterday. That sadly, our perception of desert is something which has been shaped by movies, where we see the actors and the actresses roaming around in that hot sand, and that is where we think that okay, deserts are always going to be very hot. Ladakh is also a kind of a cold desert, right? The region around Pangang So, the region around Galwan Valley, where all these clashes are happening, that is also a desert. Gobi Desert is also a desert in the region of Mongolia. It is very cold. Many portions of Atacama Desert are also very cold. So you will have examples of cold desert as well, right? So please don't get confused based upon the Bollywood and the Hollywood movies that you have seen that desert means we will die of thirst itself. Desert means that during the night it gets very cold. That is why when the winter comes in, for the first time, when the temperature starts dipping, the mercury level starts dipping. One of the lowest temperature is to be observed in the month of December is in Rajasthan, where in the district of Churu, you will always experience a temperature close to around 0 degrees Celsius or maybe 1 degree Celsius. It is a desert, but you have very low temperature, isn't it? I hope that is understood. Okay. Now, after this, we come to the portion what is referred to as urban heat island effect. What is this? Urban heat island. So, heat island means heat is restricted into that particular portion. So this is something that you would also have experienced as, let's suppose you come from the hinterland or from the region of suburbs or from a rural part, and then as you enter the midst of a city where you have large constructions, lot of buildings, etc., you will generally find that that particular portion is a bit warmer in comparison always. Why is that? So that is what is referred to as the urban heat island effect. That is basically, it is that part of an urban or a metropolitan area, right, that is marked by remarkably high temperature as compared to the rural counterpart. So you will observe, if this is what is indicative of the graph of temperature. So you will observe that as you move into the heart of the city or into the midst of the urban area, you will observe that there is an increase in temperature. So that is what is referred to as urban heat island. Whenever you move out of a dense city, densely populated city, always you will observe a kind of a cooler condition and a cooler temperature. So why does this happen? That happens because of a variety of reasons. In the urban areas, there's a large scale concretization. Lot of concrete buildings, concrete roads, concrete pavements, everything is concretized, and they end up absorbing greater amount of solar rays. The roads are dark black. Why? Because there is an asphalt coating. The roofs are also tarred. The building roofs, they have a tar layer. Why? In order to provide waterproofing. Now, all these darker surfaces, what will they do? They will absorb significant amount of heat, isn't it? So that is where darker surfaces in the form of asphalt, right, and rooftops, they will absorb greater amount of heat. Absorb larger amount of heat. Okay? Then, less movement of winds. Why? Because in urban landscape, you have such a greater concentration and density of buildings that the wind movement is also stopped. And when you don't have wind movement, the air stays in a region, it gets warmer over a period of time. So overall, the temperature also increases. Okay. Then lack of green cover. If you have a green cover in a region, that region is automatically cooler. So that is why lack of green cover basically means lesser cooling, because whenever you have more trees means more amount of shade which is provided, means lesser amount of heating which is observed. Then lack of open soil regions, this is also an important factor, because whenever you have natural land, natural ground, so if there is rainfall, let's suppose in any particular region, let's suppose, why the building is dark? Building is not dark, my dear friend, it is the rooftop which is dark to provide that. If ever you have been to any rooftop of a large building, it is always tarred. It is a kind of a coating of tar which is done to provide waterproofing. Okay. So when you have, let's suppose, any particular region, now this receives rainfall, let's suppose. Now that rainfall percolates through the soil. Now, when the rainfall is done and when it is not raining anymore, now in those conditions, what will happen? There will be evaporation. Whenever you have open areas, there will be evaporation from the bottom of the soil, from the lower regions of the soil. Water will come up, it will evaporate. Evaporation always provides a significant amount of cooling. I hope we are aware of that, that wherever evaporation happens, cooling is also associated. So lack of open soil regions mean lesser continued evaporation, which means lesser cooling. Okay, that is a significant factor. Whereas in the urban areas, you will find that all the water very quickly is redirected into the sewers and the drains, and you don't have that continued evaporation. Does not mean that the water should not be directed towards the drains, but that means there is a kind of a lesser amount of cooling. Whereas in suburbs, in rural areas, there is a lot of that natural evaporation which happens, and a continued evaporation, that is not immediately after rainfall, but maybe after 2 or 3 days later as well, you have the lower regions of the soil losing water, creating that kind of a cooling effect. In the urban areas, there is a greater greenhouse gas emission, be it carbon dioxide, carbon monoxide, nitrous oxide, etc. So, greater greenhouse gas emission means greater retention of heat, greater retention of heat. And then in urban landscape, you have a lot of that cooling devices and other electrical appliances. For example, let's say air conditioners. Now, air conditioners are used quite significantly in large proportion. Now, air conditioners, whenever they are used, they provide cooling inside, but they heat up the region outside. So that is also something which will warm up the atmosphere outside. So that also provides significant amount of warming, right? So that is why, due to all these reasons, the urban areas, they get significantly heated up, whereas the rural and the suburb areas, they are much cooler. Now, what can be the solution? You can have green buildings. Now, green buildings does not mean a building which is painted green in color. Green buildings mean which is environmentally friendly, where you don't need so many cooling devices, cooling apparatus, where there is a natural airflow. Green buildings mean where during the daytime you need not switch on the, let's say, tube lights, etc., where the natural source of light is there, right? You can have a better spacing in the buildings as well. So that is where environmentally friendly construction, reflective materials, whitish buildings, and whitish paints, they can always help in removing this particular urban heat island effect. Okay, I hope that is understood. So that is where we'll end the session here for today, and we'll take a couple of questions and then we will end it up. More questions we'll be taking up for tomorrow, because after this, I'll be initiating the webinar. So let's take a couple of questions and we'll end it up. Why in mountains solar rays get more reflected? Only if the mountainous region is covered with ice, and that is the whitish color that reflects more. Albedo Thesin is the reflective quotient of the surface, the amount of solar rays that it will reflect. That varies between 0 to 1, 1 being 100% reflected, 0 being means 0% reflected. Adnan, show the previous slide. Okay. Mapping not for today, Shivaji. And oceans wave are like stars, and what? Ocean wave are like stars, and why do it don't happen everywhere? Sakshi, I'm unable to understand the question that you are asking. Are you asking about the kind of twinkling that you get from the sea surface? Is that what you are asking? Okay. Albedo is similar to terrestrial radiation? No. Yes, Poola, you can attend it if you have to follow the portion of current affairs. South and north facing Kumar is basically which is the direction in which the land is facing. If let's suppose the land is facing the solar rays directly, it will receive more amount of insolation. So, for example, we had taken the case in the northern and the southern hemisphere. So, if you have a mountain system here, obviously, this is the portion which will receive more direct rays of the sun. So, that is why the insolation level will be higher. Is albedo and heat budget the same thing? Absolutely not. Heat budget gives you an account of the total amount of solar rays received and the total amount reflected. Ashay, what can I do for current affairs? Newspaper reading, my dear friend. And convection. Convection is, Muskan, when the heat transfer takes place by the movement of the particles. Conduction is when the heat transfer takes place when the different objects are in contact with each other. And radiation is where the medium is immaterial and the heat transfer does take place. Auroras, they refer to the northern and the southern lights, which are created as you have the charged particles of the sun. they interact with the particles of the atmosphere aided by the magnetic field lines of the Earth. How charged particles are formed? Due to the energy of the uh, solar rays. That is how they get charged, where the electron escapes the atom or electron is added to the atom. Auroras are formed in the ionosphere, yes. Okay. So, you said the animation video. Akshita, you'll find it in the portion of space hurricanes. Okay. So that is where we'll end the session here, guys. We'll take it up tomorrow, the rest of the discussion. So till